All right, so when at the beginning of the year, when I was like, oh, this year we get to do air resistance, I was excited about it because air resistance is really the first example you run into where the force acting on an object varies with the velocity, right? And I kept thinking, oh, this is going to be an awesome way for us to, use some integrals and that kind of stuff. But it turns out that it's actually not that bad because to solve sort of true drag problems, you have to learn how to solve what are called differential equations, which is count 4. So we won't be doing that. So, as a result, this section ends up being basically memorizing one equation and just a lot of plug and chug. All right? So they're not bad. I'm not going to spend a ton of time on this, all right? And I think if you look at this assignment, I think it's just one side of a sheet. Like the 6-2 assignment is very short. All right? So, here we go. All right. So first of all, I think you guys have already, hopefully in honors, have kind of talked a little bit about drag. So the idea is this, that when an object moves through a fluid, is the sciencey way of saying it. Usually you would think of it as moving through air, which is an example of a fluid, right? But this would work for water or different, different gases, whatever. All right. So if you've got an object moving through a fluid, the object has to push that, the fluid, the air, the water, whatever it is, out of the way. And as a result, the fluid pushes the object, right? And it results in a force that's called drag. All right. The book uses capital letter D for it. Again, I always put a capital F in front of it. So capital F subscript D, force of drag. Okay? Now, how much drag force there is depends on what? 4 things. All right? So the first thing it depends on is fluid density. And like I said, every time I open this up, I lose my formatting. Fluid density is not R. It's the Greek letter rho. Okay? So that's the density of the substance that you're in. You guys from chemistry know what density is, right? It's the number of kilograms per unit volume. All right? We're going to use kilograms per cubic meter. Okay? So the idea is the denser the medium, the denser the substance is that your object is moving through, sort of the harder it is to push through it, right? That's why it's hard to run through a swimming pool, right? Because water is more dense than air, right? Okay? All right, the second thing that it depends on is the object's cross-sectional area. That's why if I drop a piece of paper like this, it falls slowly because it has a large area. But if I crumple it up and drop it, it falls just as quickly as a thing that's not paper, right? Because I decreased the area and therefore decreased the drag force. Cool? All right. So the area matters. The object's velocity relative to the fluid. Okay? So a little bit of relative velocity stuff there. I think most of the problems we're going to do are pretty straightforward there. We're going to assume that the fluid is stationary, relative to the earth and you're moving through it. But the idea is the faster you're moving through the fluid, the more fluid you have to push per second, and therefore the more force it's going to exert resisting. Right? And you guys know this. If you're driving down, down Fisher, and you put your hand out the window, it's not a big deal, right? But if you're driving down 94 and you put your hand out the window, it's like, right? The faster you're going, the more area you have to move, right? Okay? And then finally, this is the piece that's a little bit dodgy. The last thing that it depends on, so with friction, there's a coefficient of friction. Okay? Similarly, there's a drag coefficient. And in the same way that coefficients of friction are experimentally determined, your drag coefficient is experimentally determined. But basically what that's going to boil down to is it's the shape of the object. Okay? That if the object is sort of more aerodynamic, it's going to have a lower drag coefficient than, if it's, like a flat-fronted school bus is going to have a very high drag coefficient versus, a Corvette is going to have a low drag coefficient. Cool? All right. So, here's the equation to find your drag force. It's half of the coefficient times the fluid density times the cross-sectional area of the object times the velocity squared. Cool? Problems there. Right. I didn't stress this idea of cross-sectional area. So if you're talking about the school bus driving, it's the area of the front of the school bus, right? Does that make sense? Okay. So the cross-sectional area is taken perpendicular to the velocity. So if it's going this way, then you kind of chop it across the middle and measure the area that way. Cool? Yeah. Correct. Yeah. Yeah. It's sort of like the maximum cross-sectional area is the way that it's generally understood. Yeah, and then the coefficient sort of deals with the fact that the shape might be irregular. Cool. All right, everybody good? Yeah.
Do you like red racing stripes lower drag?
Mm-hmm. Yeah, they totally do, because red is the fastest color. Yeah. Yeah. Good question. Very good question. That's not in a lot of books that red is fast, right? So, that's really funny. You just said that, but we just bought my son new shoes, and he's like, "I want red. They're faster." So, I'm not sure if he was joking or not. Okay, so here's the deal. So the first thing that I want you guys to be aware of is, so when you talk about drag, a concept that comes up very quickly is this idea of terminal velocity. All right, terminal velocity is, it's one specific velocity, but it's specific to an object that's in, I'm going to say free fall, but it wouldn't be in free fall because of air resistance, but an object that's being accelerated down towards, the planet because of gravity. Okay? You wouldn't talk about the terminal velocity of a school bus unless the school bus was falling. Does that make sense? Okay? So the idea is this, that when an object is falling through the atmosphere, so suppose we've got a skydiver, so here's Roy, right? So there's Roy, he's falling. All right? So when he first, steps off the ledge of the helicopter or whatever, gravity is going to be pulling him down, right? With a force of, let's say, negative 1,000 newtons or whatever it is. Okay? So gravity's pulling him down, right? Well, when he first steps off the edge, his velocity is 0 for all intents and purposes, right? So there's no drag force. So when at that instant, his instantaneous acceleration would be negative 9.8 meters a second squared, right? Okay? So, but he's going to speed up. And as he speeds up, his velocity is going to increase, right? So remember, our drag force is... right? Okay. So the idea is, as he speeds up, this number is going to get bigger. Right? The v squared is going to get bigger, which is going to make his drag force get bigger, right? Okay? So some amount of time later, his drag force might be, say, 100 newtons or whatever, right? Well, that's going to mean his acceleration at that point is going to be still a negative number, but a negative number less than 9.8, right? Does that make sense? So, let's grab a calculator and figure out what it really is. It's just going to be 90% of it, right? Because we got 90% of the net force. So 1 times 9.8. So now your acceleration is negative 8.82 meters a second squared, right? He's still accelerating downwards, but just not as quickly, right? Make sense? So a little bit later, he's going to be going faster. And so now my drag force is, I don't know, maybe it's whatever, 400 newtons. Well, gravity's still winning, right? So now my acceleration is going to be some other small number. Let's see, 9.8 times 0.6. So that gives you negative 5.88 meters per second squared. All right, but the point is, even with this drag force, gravity's still winning, so it's going to keep gaining speed, right? It's going to gain speed at a slower rate, but it's gaining speed nonetheless, right? Eventually, what's going to happen? Eventually, your drag force will cancel out your gravity, and then the acceleration is 0. So eventually, you hit a point where your drag force is equal to your force of gravity, or equal and opposite, right? And at that point, your acceleration is 0. Does that mean you stop falling? No, it just means you stop accelerating, right? And the velocity at which that occurs is called terminal velocity. Does that make sense? Right. So we are 10 seconds away from being able to figure out the equation for terminal velocity for an object. When do you hit terminal velocity? When the acceleration is 0. But why does your acceleration hit 0? So your drag force equals your force of gravity. So That's an at sign. So when you hit terminal velocity, our drag force equals our force of gravity, right? Well, so that means drag force is Fg equals 1/2 c rho a v squared, right? That's still a v, even though it doesn't look like a v. I will fix it and make it look like a v. And then I can put a little t here to indicate terminal velocity. So once you hit your terminal velocity, sorry, I'm not doing a very good job managing my board space today. So once you hit terminal velocity, your drag force is equal to the force of gravity, and therefore your drag force is equal to the force of gravity. That's 1/2 c rho a v terminal squared, right? That's the point when you're going to stop accelerating. So do a little bit of algebra here, and you can find that v terminal equals, what's it going to be, 2fg over c rho a all square rooty. Now, your book lists this equation and this equation separately. If I were you and I was studying for the AP test, I would think that seems like 2 equations to memorize. That's too many equations to memorize. So I just memorize this one, and then if I need to find this one, it's easy to find, right? You just put in your force of gravity for your drag force, do some algebra, right? Make sense? Questions? All right, so I will use this equation. If I think today I'll use this equation since we just came up with it. But for the most part, like as we're doing if we go over homework problems, I'll probably, anytime there's a terminal velocity equation, I'm probably still going to go back to this. You know, work backwards. All right, cool. All right, so I think is this the only example I put in here, I think? All right, this is the best example you're going to get from me all year. Are you excited? All right, so here we go. According to a random unsubstantiated website that I found, a 30 caliber bullet has a terminal velocity of 90 meters per second. It says, suppose the mass of such a bullet is 8 grams. What am I going to do? Kilograms, very good. And it has a diameter of 7.62 millimeters. What am I going to do? Meters. Then it says the air has a density of 1.2 kilograms per cubic meter. Then find the bullet's drag coefficient. So, we've got 2 equations that we can use, right? But I'm looking at this and I'm thinking, ugh, if I want to solve this for drag coefficient, that's a lot of algebra, right? Solving this for drag coefficient is not quite as bad, is it? All right, so like I say, I like this equation better. All right, so here we go, let's do it. So FD equals 1/2, oops, 1/2 C rho A V squared, right? So when we're at terminal velocity, well, here, so we got to solve for C, right? So let's do the algebra. So C is going to be 2FD, oops, over C, no, what am I trying to do? Times 2 divided by AV squared, right? Wow. Struggles. How am I forgetting? Rho, geez, thank you. I was forgetting something. All right, so we good up to there? All right, so plug in our numbers. Let's see. 2 times, well, FD, what should my drag force be? 9.8 times my mass, right? Right? Over my area, how do I find the area? pi r squared, right? So let's see. Let's go over here. This means our radius is going to be half of that. So 0.00, what's that, 381? So my area is pi times that squared. Oops. I think I didn't actually figure it out. I think I just left it like that. However, I am realizing this is frustrating because I did this problem twice. I did pi d squared instead of pi r squared. That was stupid. So my answer on the sheet there is wrong. Damn it, I did this twice too. This is so frustrating. That's a point, that's a point. Okay, although I did catch it before we went through it, but I'll give you the point anyway. All right, so anyway. Easy there. That was harsh.
No, I was just saying 3 points.
Oh, I gotcha. So there's our area. Our velocity is 90 meters a second. Don't forget to square it. And then my density is 1.2 kilograms per cubic meter. So we're going to have a smaller area, therefore a bigger drag coefficient. So we're going to get 4 times what I got up there. So whatever that is. So it's going to be somewhere in the neighborhood of 0.352. It's the density, 1.2 kilograms per cubic meter. Sorry, my board kind of got squished. Cool. So that means that this guy up here is wrong. Yeah, I said that a second ago. All right, are we good? Rub it in. It's fine. All right, are we good? Okay. So then B says what would the drag force be? So now all you're going to do is you know your velocity. You just found your coefficient, right? So you just literally plug in your numbers here to find your drag force, right? Okay, so let's do that real quick. Are there questions with what I did for part A? All right, so for part B, we're going at 25 meters a second. We'll do B in blue. So drag force is 1/2 C rho A V squared. So 1/2 the coefficient we just found, it's 0.352. Oh, notice, sorry, I forgot to talk about this. The coefficient doesn't have units. It's just a ratio, like coefficient of friction. Okay. Let's see, our density is 1.2 kilograms per cubic meter. The area is that mess that we found before, so that's pi times 0.00381 meters squared. And then times my velocity squared, and the velocity is 285. Don't forget to square it. So let's see, I've got 1, 4, hang on 2 seconds, so go away, 10, 4, so my answer there is actually right, by a weird chance. Yes?
So, why would you have to do that entire equation? Why can't you just go to the first one and be like, oh, that's FB there, so we have to there?
Because they're different speeds. So the drag force in the first one was when we were going at 90 meters a second.
I see.
And now we're going much faster, so our drag force is going to be much bigger.
Sorry.
No, don't be sorry. It's a good question. Sorry, no. All right. Something wrong, Kurt? You sure? Okay. All right. So I think, if my mental math is right, I think this actually still gives you the answer that I have on the sheet. Because I had too small of a drag coefficient, but too big of an area, and I think the two mistakes cancel each other out. So somebody can double check that if they have a calculator handy, but it should. Is it? Okay, 0.786 newtons. And then to find the number of G's, you just divide that by the weight of the bullet, right? So it turns out to be about 10 G's. All right, questions, you guys? Yeah, just by dumb luck and the numbers that I gave you. Yeah, so I wouldn't, as a rule, that's not true, you know what I mean? Like, don't remember that, oh, well, no matter what the drag coefficient is, you always get the same drag force. That's not true. Yeah.
So if you're on like a train going 80 meters per second and shot it, would it just kind of like stay there?
No, so what would happen there is, So, right here, so if you launch a bullet horizontally at 90 meters a second, is that what you're saying?
Yeah.
In that case, you've got the object moving forward. Your drag force would be negative, whatever, and so it would just slow down. It wouldn't stop immediately, but it would slow down quickly, right? Because there's nothing pushing it forward. The drag force would be slowing it down. Does that make sense? But as it slows down, the drag force would get less, and so it would slow down at a decreasing rate. Does that answer your question?
Yeah.
All right. Are we good? Questiones. All right.
What are we in, chapter 6? CH6, 1 point, notes 6.2. All right,
We're pretty good.
all right, we have got 15 minutes. I promised you concepty stuff. Let's do some concepty stuff. Why don't you dig out a phone or some sort of internet-happy device? Thank you. I guess I can record this. All right, here's what I want you to do. Dig out a phone or smartphone or something, and go to response.smarttech.com. Really? I thought you guys would be excited.
We used to use this for tests. It's a great test.
Oh, right. Yeah, and I understand how that went.
These tests are so
Oh man, it's gonna be good.
I tested it to make sure. Okay, there you go. All right, so here's your assessment ID. All right, that's one more thing that I don't have time for. I wouldn't be surprised if Kahoot had AP level questions. Maybe they do. They might. Oh, I gotcha. All right, so a lot of these questions, some of these are questions I wrote, and some of them are questions that are drawn from basically the same test bank as where I get the test questions from. Okay? So there should be some similarities in the way these questions are worded to the stuff you're getting on your tests. All right, is everybody logged in? Or no? Can I close this? Everybody got their ID?
Yes.
Oh, I forgot to start the question, didn't I? Where's it going? It's going? Oh, okay, cool. All right, so this one's going to take you some work. This is on the hard end. Some of these are quicker. This one is definitely one that you're going to have to sit down and do some calculations on this. Okay? Made particularly difficult because there aren't very many numbers. Well, there aren't any numbers. All right? This is how the AP test is going to be, you guys. There are going to be problems like this with no numbers, and you got to come up with expressions for stuff. So, see what you can do. You're going to want paper and pencil. You probably don't need a calculator. So since you're going to want to study this, I would write down sort of the pertinent information that you're given, like, oh, the velocity is constant. Oh, the coefficient of friction is mu k. Oh, whatever. Go from there. I would not be surprised if this is the only one you have time for today. The other ones are a little quicker. Just happens to be first. Yep. Yeah, when you're done down at the bottom, there should be a little submit button. Oh, look at that. was probably the right answer or not. I hope not. Ah, that's good. Yeah, you must have left the website or something and come back in. Oh, you're cheating again, Alex. So I'm looking at that. Sorry. Yeah, I should have said that. I do have a set of clickers, you guys, if you don't have internet-friendly devices. Two people are not logged in.
Patrick's not getting.
No, but there's 27 people in here, and it only shows me 25 people signed in.
My phone's dying.
Oh, I gotcha. Okay. Okay. He's still solving the problem, though. Still solving the problem. Anybody else? I don't mind. I'm just curious what's going on. What's that? Laptop died? Okay. All right.
You should break that.
You fixed your phone, I said.
Oh, it wasn't mine. It was his.
Oh. The wonders of masking tape.
Oh yeah, that's good.
What's up?
If you use the latch.
Oh, right, because an electrical device. Good thinking. If we break a duck, we can use. Sorry.
That was dark.
You guys are the ones that are impaling the ducks. All right, this is maybe not going to be the best use of our time, because a lot of you are sitting waiting, huh? All right, we will figure out another way to do this. No. You know what, maybe I'll do next time. Maybe I'll pass these out like the day before. You guys can work on them, and then you can yeah, do that. Oh, I don't know. Okay, anybody need another minute? Can I stop it? All right. Stop. Okay, so what's it going to do? Oh, there it goes. Okay. Yes. Oh, wait a minute. Oh, no, sorry. Okay, all right, cool. Yeah, so correct answer is C. Okay, so somebody got it? Want to come up and explain? What do you want me to do? Am I just doing it?
If we got it, But we didn't get it.
I understand why.
Don't get it? All right, let's do it real quick. All right, so check it out. Yeah, so we need to figure out a better way to do this. All right, so here's the deal. Here's your ramp. It's inclined at an angle theta. All right, and there's this horizontal force, right? And the question is, what's the normal force, right? All right, so the key thing, you guys, is knowing that it's moving at a constant velocity. So that means that our net force on this thing has got to be 0, right? All right, so there are a total of 3 forces affecting the net force. All right, so the box is moving up the ramp. So there's going to be a force of friction kinetic. There's going to be an FG parallel, right? A parallel component to the gravity. And then if this guy here is F, there's going to be a parallel component to that force, right? So what we want to do is we want to write expressions for those 3 things sort of in as much detail as we can. All right? So let's look at the F first of all. So the idea is, here's the ramp, here's my force F. So the idea is there's going to be one component that is parallel to the ramp and one component that is perpendicular to the ramp. Does that make sense? And I know this angle here is theta, right? So my parallel component is just going to be F times the cosine of theta, isn't it? Okay, so this is F cosine of theta. Does that make sense? All right, and FG parallel, we know that. FG parallel is just FG times the sine of theta, right? Good. All right, so this will actually work today. Ooh, neat, that hasn't been working all day. All right, so here's our statement. I need my net force to be 0. So that's going to be equal to my force of kinetic friction plus my FG parallel plus my F parallel, right? So let's see. We're going to get 0 equals, oh, I haven't dealt with this force of kinetic friction. We're going to have to come back to that in a minute. Force of kinetic friction plus, let's see, FG parallel is going to be negative FG sine theta. And our F parallel is F cosine theta. Follow? All right, so we're still not there, though, because we're trying to find the normal force. The normal force isn't even in this equation anywhere, is it? It's hiding somewhere. Where is it? This is my coefficient of kinetic friction times my normal force, right? So if you solve that for normal force, you get option C. Make sense? All right. There, like I say, on the AP test, there are going to be problems like that. They're very abstract. Like, there's no numbers here. What do I do? Okay. All right. Good. All right. Oh, so there's the answer. All right. Let's do this one. This one should be quicker. We have time to do this one, I think. Oh, I will embiggen it. Should pop up. Just give it a second. This is another good one. No numbers, but enough information to solve it. Yeah, no worries. No, you're good. Don't worry about it. Oh, it tells me how many I've answered. Neat.
bell's gonna ring here in just about a minute, so I'm gonna get your answers in. I'm clicking stop. Oh no, sorry, I didn't mean to call anybody out. Okay, so correct answer is, does it tell us? Oh, the green one. Oh, right, duh, that would make sense. Okay. Yeah, so here's the deal, you guys. They're all the same, made out of the same thing. Pine blocks are all on the same surface, so they're all going to have the same coefficient of friction. The normal force is going to be the same because they all have the same mass, therefore the same weight, therefore the same normal force. Clearly, block 3 is the biggest area, right? I guess I shouldn't say clearly, but it's supposed to. If you discover the horizontal force to get block 1 moving, then it's going to be the same for all of them, because they all have the same normal force and same coefficient of friction, right? So the only one that doesn't make sense is B. They should all have the same magnitude of force of friction. Because either it's moving or it's not. If it's moving, then they all have the same kinetic friction because they have the same normal force and same coefficient. And if it's not moving, then the friction is 0. Kinetic. All right? Okay, I will find a better way to do this so it's not quite as much dead time, but I hope that's a step in the right direction. Tomorrow will be a cartoon/work day. I promised you cartoons, but you might use the time to work. Have a good day. Test, I wonder. You're here for the test?
Yeah, I got it.
Oh, you gotta finish it. That's right. You already started it. This. Y.
V equals x squared plus y squared square root of 5.
You can't read that. No. There you go. Good luck. Let me know if you need anything clarified.
Right.
Oh, good. That's what I was looking for. Give me 2 more seconds, Maddie. Don't go away. Come on, computer. There. Boop. Boop. Okay. Oh. All right. What is your feeling about how ready people are feeling for the test? Not bad.
People are pretty ready.
Didn't know if you heard people buzzing.
No, yeah, I mean, I think this was a good, review. I mean, other than, number 6, I think everybody else got, most of the...
Okay. 6 was hard, for sure.
Yeah. So for some reason, I couldn't figure out what 4.
Okay.
That's, what I... 4B is the same thing except without stuff.
Right, well, but there's an important difference, because in 4A, good, yeah, you want your acceleration to be 0.
Because it wants the static.
Oh, I like your way of solving this better than the way I explained it, to be honest. Curiouser and curiouser. Okay. Right, so for A, you're trying to find the coefficient of static friction, right? Okay, so tell me about your drawing here. What's going on?
Okay, I just drew in the force of gravity.
Yeah, good.
And then I didn't know, so then, and then, I don't know, I drew the force of tension force, tension sort of like,
I gotcha. So I love what you've done. This is easier than what I was thinking. Easier than the solution I showed in class. So remember, the tension at both ends of the rope is the same.
okay.
Hello, it's Mr. Eckert. Hey, what's up? Want the test? You think it's manageable? Say that again. Okay. Uh-huh. Okay. I just wanted them to understand that there's room for it to go up or down. Okay, so if I just said, maybe I should just say on the ramp instead of halfway. I can put a picture in, I mean, whatever, it's a block on the ramp, that's fine.
Yeah, I've tried it before.
I gotcha. Okay, I can do that. Okay. Block. Yeah, no worries. It was easy. To be honest, most of the problems were from one that I gave back in Farmington. I tweaked a couple little things here and there, but okay, cool. Thank you for looking at it. Yes. Yeah, it's worksheet 4.4. Ooh, do this though. If you're gonna give it, do you have a pencil to write this down? I haven't had a chance to change it yet. On problem number 5, change the coefficients of friction. The way that it's written, there's a really weird, freakish coincidence that confused a lot of my students. Anything else will work. So right now they're set at 0.48 and 0.36. Why don't you change them to like 0.36 and 0.24 or something? But that just means you'll have to resolve them. I don't remember. It's been weeks since I did that one. What was it? Can you refresh my memory what the problem was? Oh, yeah. That does vaguely ring a bell. Yes, that does vaguely ring a bell. And you might be right, yeah. Yeah. That vaguely rings a bell, yeah. Do you guys have worksheet 4.3, Andy? Was there a mistake on that Scooby-Doo problem? Bottom of that ring a bell with you guys?
It might.
Which one was Scooby?
Oh, the answer wasn't even on the sheet. That's the problem.
Yeah, I got
Yeah, 700 something.
Yeah, I remember that answer too.
Okay, yeah, so just the answer isn't on there. And it's supposed to be like 700 units-ish. Good. Right. Yeah, yeah. No, I think they need it. This is definitely the hardest section we've done. So if they struggle, then I think we'll take some word for it. Okay, I will talk to you later. Yep, bye. Alright, sorry. Okay, why don't we all, can we turn and make like a little circle here or a little physics powwow? Okay, so real quick too, while I'm doing this, you guys, I want to get this quick to get for time. By all means, let me know if you can take a test after break. It's not a big deal. I think most people prefer to get it done beforehand. Forget it all over break.
And if you're not ready, then you're better to spend the time studying and do better. You know what I mean?
Right.
Okay, so let me finish up. So,
Cool, right?
Maddie and I are doing number 4 right now.
I think we did that one in class. Yeah, you guys did it 4 times.
Yeah, we didn't get through it in 6 hours. So let me finish explaining it to her real quick. Is that okay? All right, and actually, to be honest, Maddie showed me, did it a different way than I did it, and to be honest, it makes it makes it easier. Okay, so I don't know if you guys remember what I did, is I looked at the system as a whole.
Yeah, that confuses me when you do it for police because it's like a big block.
Yeah, I know, it's weird.
My thing is, you know, because you can't just like combine the boxes.
Right. I know what you mean. Yeah, it's confusing because you got to think about like what forces from each individual box or on each individual box come from outside the system. You know what I mean?
So confusing.
Yeah. Okay. So we'll do some of this. All right. So, but before we do, so here's where we're at. So I'm going to draw this so everybody can see. So here's Jackie Chan, right? And his shoelaces hanging, and then down here we've got Jet Li, right? Cool. All right. So what you did, so when I did this, I looked at the whole system, and what I said was, okay, well, I know that the force of gravity down here is negative. What is it? 637.
Wait, I have a question. So is that just the weight times just of Jackie?
Yeah, because Jackie Chan's force of gravity is on the platform and it's not going to cause any acceleration in the direction of motion. Make sense? All right. So what you did then was you said, oh well, I know that Jet Li isn't moving, right? So that means that my net force has got to be 0, which means that the tension on him has also got to be 637 newtons, right? Good. All right. So what I was trying to say to you as the phone rang was this. So remember, the tension in your rope is uniform. So if the tension is pulling Jet Li up with 637 newtons, then it's pulling Jackie Chan forward with 637 newtons.
So then the force.
So that means that your force of static friction over here can be as big as 637 newtons.
Okay, and then you can do 637 equals.
And then, yeah,
And all force is just the key.
well, we gotta find it. So now for this guy,
Oh, so that's what we have to
so
do.
now we've got 70 kilograms, right?
So wait, did you find the force of friction static mass?
No, that's what we're trying to find.
You were talking about the coefficient.
Well, right, but in order to find that coefficient, you have to know the force of static friction mass.
So how did you know that it could exert that much force?
Well, I guess I shouldn't say that. It needs to exert at least that much, right? Because, so you're trying to find the minimum, oh, this is going to be weird, because we're going to have minimums and maximums in the same problem. I hadn't thought about this in that much detail. So, I want to say this. So, gravity's pulling Jet Li down with this much force, right? That means my tension is this much force, right? That means my tension over here is that much force, right? So what that means is that my FS max, in order for him to not move, it has to be bigger than or equal to 637 newtons.
It's just by knowing that he's not moving, he's knowing that the static friction is not moving.
Exactly.
Right, so how
And
did
so
you
far-
cancel that pressure piece?
Right. Say that again, sorry.
How did you know the net force was 0?
Because he's not moving.
How did you know that?
Because we're trying to prevent him from slipping off the thing.
The minimum coefficient of static friction.
Yeah.
Okay.
Do you see it?
So then you find total force just for this box, just for
Correct.
this box?
Correct. Because the static friction is just acting on this box.
Okay.
Follow?
You said normal force, but
Exactly.
when I was solving it, I was like, there's too many things to cancel, and I was really confused. And then I had my cousin help me, and he was real weird, like, equations that didn't make any sense. He didn't know what he was doing. Like, fantastic.
Gotcha.
And then now it makes more sense. It was just missing, like, I knew it was two things to find, but then I like didn't plug it in the right way.
I gotcha.
The picture, when it was lost.
That's where the system is confused, because you said the normal force, but it's only Jackie Chan, right?
Yeah, so I mean, the normal force doesn't sort of affect the system because it's perpendicular to the direction of motion anyway. You know what I mean? So like usually when I'm looking at the system, I just look at the forces that are going to affect the motion. Now sometimes though, like if friction is one of those forces, then you've got to find that normal force to find your friction. You know what I mean?
But it's just the normal force of friction.
Correct, because he's the only, of the two objects, friction is only acting on Jackie Chan. It's not acting on Jetly. Jetly's just hanging there, there's no friction.
Then can we do Ewan's frictionless?
Yep, so before we do, is everybody okay with A? That's a tricky problem, for sure.
It makes more sense second here explaining it. Like I get it a lot more now than I did in class.
Okay, I think I was a little rushed to class today, so. You think you're okay? And
Yeah,
I didn't finish my drawing, so here's your gravity on Jackie Chan, and then here's your normal force. Right? So that's one for that diagram, that's one for that diagram.
Okay.
Cool? All right, now part B is literally the exact same thing we did before.
Okay.
Okay? So for part B, you've got a ledge with Jackie Chan, 70 kilograms. So this is like your cart and a rope, and then your hanging mass is Jet Li, 65 kilograms.
So we just take that divided by.
Take what and divide it by
Take
2.
the force of gravity on the jet.
Yep, so that's negative 637.
Okay.
And then divide it by,
Just gently or not?
what do you think? So what
Oh,
this
the whole
one,
thing, this whole thing.
yes, and you explained it the right way too. The idea is this one force is, it's not just affecting Jet Li, it's also affecting Jackie Chan, because the whole system is going to accelerate this way.
Okay.
And so this force is affecting the total mass, the mass of the whole system.
So then you don't have to worry about friction, no problem?
Well, yeah, could have, and in retrospect, I wish I had asked you to find that force attention.
Wouldn't it just?
So let's do that. So here, so finish the problem, find the acceleration, and then let's all find that tension. There are 2 ways of doing it, and it's probably worthwhile to do it both ways. This wasn't on the homework. What's wrong? Heavy.
Find only the force of gravity of jet and use the form.
So what other forces are there? There's no friction, and then your gravity here and your normal force here cancel each other out.
But if you find the tension, does that affect the acceleration?
It doesn't affect the acceleration of the whole system because this is, I should have put a multiple choice question about this. I didn't, so. But the reason we don't need to worry about the tension here is because it's an internal force. So if you're looking at the whole system, this is why I keep drawing those sort of nebulous blobs, because I want you to understand that the rope is now part of the system.
Is that like when you have like a pinata or
No, I mean, well, so you can define a system to be whatever you want. Like you can pick, every collection of objects in the universe and say, my system is this. You know what I mean? But so for us, since we're trying to find the acceleration of these 3 things, the 2 dudes and the string connecting them, we make that our system. And then we say, okay, well, what forces are coming from outside of that system to make it move?
So since the force of the tension is inside the system, it doesn't affect the acceleration.
Of the system. Correct. For the same reason that if you run out of gas, you can't sit in your car and push on the dashboard, right? I keep saying that example, but I mean, that's exactly what that is, right?
Basically, is this based on like constant pressure?
They sort of cancel each other out. So like, the idea is, it's pulling this object up in a negative direction, but it's pulling this object in a positive direction. So those 2 forces kind of cancel each other out.
Okay.
With the car example, it would be this. Look, if I push the car forward, then the car is going to push me backwards, right? But then, sorry? Yeah, but then, so the idea is, so then, now I'm being pushed into my chair, but the chair is pushing me forward. Cool?
Yeah.
All right. So when do we worry about the tension? I want to make sure you get it. So we don't need to worry about the tension here because right now the system. Good. he in danger of falling off the ledge? Well, it's frictionless, so there's nothing to help him. What's working against him? The tension is, right? That's the problem. So if you're just looking at your system, if you're looking at your system as being just Jackie Chan, then the tension's an external force, right?
Oh,
Ding, ding, ding,
so
ding,
you're
yeah,
like
so it's
saying
ejected,
that
right?
like throwing holes around down.
Does that make sense? So like if you're just looking at Jackie Chan, he's like, whoa, the string is gonna pull me off the ledge, I'm in trouble, right? Follow? Everybody?
Well, I'm gonna answer on it.
Yeah, that's correct, yeah. I did that. Cool?
Yeah.
Alright, so now that you've got your acceleration, so Maddie just found the acceleration she got. It's like 4 point, is it 4.7 or like 4.6 repeating or
7.5.
so it's about 7. Right? So there's our acceleration. Everybody okay with how she got that? Alright, so now find the tension. And there are 2 ways of doing it, and I think it's valuable to do it both ways. So here's what I want you to do. Here's the easiest way to word this. Make a free body diagram for Jackie Chan. Make a free body diagram for Jet Li. It's this way, however you want to call it. Again, it's frictionless. Yeah, it looks. Oh, should I have a contradiction here? I have positive and negative. So let's make it positive. Doesn't really matter. Polka dots, plaid, it's not good. All right.
That's in the book, it's a navy blue.
All right. I just bought those pens. Well, no, the force of tension is the force of the rope. So you're trying to find, when you talk about force of tension, the definition of tension is the force exerted by a rope or a string or whatever. So what 2 objects is the rope pulling? Right, so we're trying to find the force of tension on Jackie Chan and the force of tension on Jet Li. They should be the same. Correct, yeah. Because they work against each other. Or they work in different directions.
I don't know, I thought I was doing something, but now I think I need to start over.
Okay. So are you doing Jackie Chan or Jet Li first?
Can,
Okay. So tell me what you did.
so, since acceleration, I want to find the net force. And then I kind of hit a dead end because I figure, like, force of gravity we need but just the still, so just the force of gravity still cancel out with normal force?
Exactly, yes.
Okay.
So what's your tension?
Is our tension just the net force? Oh!
Yeah, because that's the only
why I
force
hit
that's affecting the motion.
dead end, so-
All right, you all set?
Yeah, I know you're
All right.
Alright.
Make sure you have the video watched for tomorrow, yeah?
Yeah, I do that.
How's that working for you? You like that or no?
Oh, way better. Yeah, I get it a lot better. I think it's just because I pause and listen to the goals.
Okay, cool. Yeah, I wish I'd done that from the start. I second guessed myself and just my regular class.
So, how they're doing like now,
Yeah.
just so with Jackie Chan, I think normal force cancel out, so the only force you have is the one that's going right.
Tension.
Oh, okay. So that's just the net force.
Uh-huh. So what'd you get? Okay, cool. That's what you got too, right? All right, so now, once you've done that, now make a free body diagram for Jet Li. Are you good?
Yeah.
Molly, how about you?
I'm there.
Okay.
And it's different for Jackie Chan because,
Wait, for this guy named?
yeah, or Jet Li.
No, you're okay.
We got 329 for this one. Right?
Uh-huh, yep.
But then for this one, you get a net force, it's negative 300.
So then you're right, the net force is different, but find your tension.
Right, so then, would you just have to do this plus
You got the right idea, but actually do it. I want to see you do it.
the 3
There you go. Yeah, that's better. Because the acceleration's around it. They should be close though, right? They're both like 330-ish.
That's what I got originally, but then when I heard him say 3.9, I was like.
I gotcha. Yeah. Yeah, it's just a rounding issue. That was why, I don't know if you remember, I asked you what this was exactly, right?
Yeah, yeah.
And even this wasn't exact, so it makes a surprising amount of difference.
Oh, I think 31.
Yeah.
So what do you
It's
add
just a rounding issue.
to the net force? Like, what's the force on,
Okay, so there's two forces on it. So do you mind if I draw on your paper?
no, go for it?
So-
Yeah, because I don't know what the other force is.
All right, so all of this is for jet Jan, right?
Mhm.
And all of this is for jet Lee. Okay? Now, there are two forces on, so there's actually three forces on Jackie Chan, right? There's the tension and gravity, but why don't we need to worry about gravity?
Because it cancels out with normal
Because
force.
it's a normal force, so we don't care about those things, right? But what about gravity on jet Lee?
Oh, okay, so that's still,
There's still a force of gravity, right?
okay, yeah, that makes sense.
So let's find that force of gravity. What?
I think I have a really hard time like reading your not like how like you add extra steps that make it fun, like that's not really an issue. But like just the questions I know they're asking, like knowing what to draw. You know what I mean? Like and what components or whatever to find.
Right. So, hang on, I'm not ignoring anything about answering that question. Are you good? Did you get it to work?
Yes, I had it.
Molly, you
Wait,
good?
so I have the net force, but that's 306.67,
Yep.
and then from there, how do you get the,
So make a free body diagram for jet Lee. So what forces are acting on it?
the force acting on it?
Good. So find your force of gravity. Yes. And the tension's the thing you don't know. Do you know anything else? There's at least one other thing you know about the big three. I don't know what you know.
Well, we have the acceleration.
Yeah. So why do we care?
Plug it into something.
And it's always the same thing. Every time you know the acceleration, this needs to be like,
Can you find the net force with that yet?
Yep,
Okay,
yep.
But, okay, so that's what I did, that's what I used,
and you got like 3.0 something, right?
okay, yeah.
Okay.
And then, I just do,
Uh-huh.
the equation, oh,
Anytime you're missing a force, like if it's like,
Right.
what's the force of tension, or what's the force of friction, or what's the,
Right.
that's how you do it. You find your net force, and then write an expression and solve for the missing force. Good.
yeah, I keep missing like that one little step,
One
like,
little
I know
step,
it's there, but then I can't remember when it's the problem,
Yeah.
and so that's it.
So, Abby, to answer your question, I don't have an immediate answer. The best I can say is, so you need to sort of ask yourself, what's the object in the problem doing, right? So if it's sitting on a flat surface, then automatically, gravity's going to be pulling it down. There's going to be some sort of normal force, right? If it's on an inclined plane, then, immediately draw your components.
And then when it's on the inclined plane, the perpendicular is always the normal force.
Correct, yeah. Yeah, those go in opposite directions from each other. If it's hanging from a rope, then there's going to be gravity and tension. I guess that's kind of it. And so then you ask yourself, all right, well, what other forces are on it? Is Roy pushing it? Is there tension on it? Is there a weird lawnmower handle acting on it at some weird angle? You know what I mean?
When do you draw the triangle and when do you find the component?
Drawing the triangle is the same as finding the
Well-
components.
Oh,
Or maybe you're asking a question different than what I'm answering.
like, you know how we find,
So there's two different kinds of components you can find. If you're on an inclined plane, then that's when you use the FG perpendicular and FG parallel equations, right? So those are components, but they're parallel and perpendicular components, all right? The other scenario would be if you've got something on a flat surface, but you've got, some weird force at a weird angle. There, you're still finding components, but instead of finding perpendicular and parallel, you're finding x and y components. So there's going to be an fx and an fy, which combined give you f.
Can I have that?
100%. Here, hold on. I will make it even better. Whereas if you've got this, then your axes are parallel and perpendicular. So then you say, oh crap, that force of gravity isn't on either of my axes. So you find your perpendicular component and your parallel component. Here your right angle's here, and this is your angle.
Question about,
Here, hold that thought for 2 seconds, you okay? No, theta.
so, like, you can draw, like, parallel going that way if you make it positive.
Say that one more time.
You can draw parallel, like, going this way if you make it really positive. Like, going
So-
up.
Like this way, you mean?
Yeah.
I mean, it's always going to go downhill. Whether you call that positive or negative is totally arbitrary. You know what I mean? Like, so I would probably, drawing this, I would probably call this negative and this positive. I don't know, maybe not. It doesn't matter. Whatever. It doesn't matter. Just once you decide which way is positive, stick with it. Cool? Yes.
So these are, we didn't do CUV in class 6.
Uh-huh.
Do these, okay. I used like the values I got with it. It's really similar. to-
Yeah, it's super similar. Yeah, no, I remember. I'm just trying to remember if those numbers look
Except
familiar.
for where it's correlated to-
Sorry. Yeah, that's right. Exactly. Window. Yeah. And like I say, there's nothing this hard on the test. This is everything.
Okay, so then in terms of like, studying for this, would you just recommend going through the other worksheets or like?
I would go through the other problems on this worksheet,
Is
and
this
then,
one, like the best resource to use, or should I use like
I mean-
the individual, because like this one has like combination of
Right.
things.
and the test does a little bit. I think the test is a little more straightforward. I think that everything on this, I think everything on the review is reasonable except for number 6.
Okay.
And then I guess to compensate for the fact that you're not going to look at 6 in too much detail, I would look at worksheet 4.3. Those are the two that I would look at the most.
So
There's
there's
probably not going to be.
4.4 and 4.3 are the
Are there not going to be many problems like the one where it's like the force of the
No, you should know those, but that's a really good example of that kind of problem.
Is there going to be like more of this kind of stuff, like in general? There's only like one problem with that. I mean,
Yeah, so you need to know how to do problems where there's a force at an angle. You need to know how to do inclined plane problems. And you need to know how to do systems.
okay.
But I think that the problems that deal with each of those things are relatively straightforward.
Okay, like like a typical problem on like one of the worksheets and that. Okay. And then is it going to be mostly show your work kind of stuff? Like you give a
There's only
problem?
5 multiple choice
Okay,
questions.
so it's going to be mostly like math.
Yeah, mostly problems, yeah. All right, you've been waiting super patiently. Thank you for waiting.
So like, on 5, and in general for these kind of problems, like, how would I know when to use,
Static and when you static.
no,
No.
when to use like,
It's okay.
parallel versus perpendicular, because like to multiply, you have to subtract from my, friction. It's like, I could get the answers if I kind of like worked backwards
I
from
got you.
them.
Okay.
But-
So really, when you're doing an inclined plane problem, why am I drawing my ramps backwards? All right, you're good?
Yeah, thank you so much.
You're very welcome. I'll see you in the morning. Or whenever I'll see you.
It might be in the morning, but.
Okay, yeah, and I'll be here by, I think I'll be here early. I'll be here by 7:05.
Okay.
You're welcome. So like I was just saying to Patty, there's sort of 2 axes, right? Your parallel and your perpendicular axis.
Yeah.
Okay. Always, your parallel component will go down the ramp. That's what causes the box to slide down the ramp, is this guy.
Okay.
All right? And your perpendicular component goes into the ramp. All right? Really, the only reason you need this guy is because
Normal force?
your normal force is going to be equal to that.
That makes sense.
And the only reason you need your normal force,
Because then,
because that's what determines your friction.
okay.
Once you've got your forces of friction, you'll never use these two guys again.
Okay.
Does that help?
That makes it a lot clearer. Okay,
Good.
yeah. Yeah, and I think I'm good on that one, except for, I kept getting like, 121 for a whole bunch of things. I don't know if that was like,
Number 5.
yeah.
Number 5, I'm sorry, but it sent me over the edge. Yeah, I went off the deep end.
So-
I was at Starbucks doing homework from 1:30 to like when it closed at 10 last night.
Sorry.
And I was trying to do this and I was just like, no, these coincidences are not.
So the coincidences were just that, they were coincidences, but I mean, if you,
If they weren't, what would you look at to then find those answers? Like,
I was confused because I was like, so I didn't realize there would be coincidences at first.
Right.
So I was like,
that was
okay,
the only
so how
problem.
is the friction kinetic being, is the.
That was why I made that announcement, because I didn't want you guys to make those connections. It's just total random chance that they happen to be those numbers. So I don't know if you just, Mr. Hernandez called, he hasn't assigned this yet. And I told him, change your coefficients of friction so that happen. And then you would just solve it. I mean,
So can we do B and C just to like clarify 5, B and C?
are all three of you guys 4th hour? Okay, cool, yes. And in my 6th hour, I did the whole problem. And I recorded it. So I haven't posted it yet. One of you guys remind me as you're leaving to post that last video.
So then I can just like.
No, I'm happy to show you how to do it.
Okay.
But I'm just saying, I'm just letting you know that it's there if you want.
Okay.
Okay,
So I just
so,
need B and C.
Alright.
Center to that edge if we do it.
alright, so you should start out with a drawing that looks like this. Right? So, are you guys all okay with being able to find these 3 dudes?
yeah, like I can't get that.
So this parallel component, if I remember right, comes up to be negative, is it 283?
Yeah.
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 And then
4,
7.
4, 7.
Wait, did we?
No, I did it, it messed out. Alright, and then your FG perpendicular ends up being,
Yeah,
37.
337.
I got
and then this one's positive 337. Okay, so as we're solving the problem, everything that's drawn in red right now will not change. What's that?
2826, so.
Copy mine?
Yeah.
Alright, so that's going to be constant for the whole problem. Alright, now the next thing you want to do is somewhere off to the side figure out your force of static friction maximum, which unfortunately ends up being 162 newtons, and find your force of friction kinetic, which turns out to be 121. Cool. So the unfortunate thing is that these two numbers happen to add up to 283, just by freakish coincidence.
Oh, I didn't even.
Okay, and that's why all that nastiness happens. Okay, so are we good with this?
Yeah.
All right. So question A, what does it say?
Find the accel, or does it move, and if so, find the accelerator.
Okay, so see if you can walk me through how we would answer that question.
So, after you find the static max, it's not enough to battle
No, that's good. I like the use of the word battle.
battle force of gravity parallel, so you know it's kinetic, and then you draw it going up the ramp.
How do you? Yep.
Parallel is pushing it down.
Because it's
Not
going to
pulling
move.
it down.
Because it's going to move down. Oh, sorry.
And then the normal force and the gravity and perpendicular cancel out, so then you just find enough force by adding those two together, the friction and
The negative parallel and the positive friction gives you a net force.
then you just do net force by the,
That's it.
you get negative 3.6.
All right. Are all three of us good with that?
I got 2.69. So
Instead
I don't know
of
what
what?
I got that for.
I wonder if you flip-flop these two guys. That's my
Probably.
guess.
Probably.
Haven't you ever written down, you know what you did?
So I did like, I got 121.3 over 45 kilograms, like up there. I don't know
So
where I got.
121.3 is probably your kinetic friction. So I wonder if you just looked at kinetic, oh, you know what you did? You forgot your parallel component again.
classic.
right? Wasn't it, you had said you had done that on one of the other problems, right?
I used the wrong one sometimes, where I used perpendicular instead of parallel for some friction ones, but now I get what I use. Never use the perpendicular for
Right,
my
yeah, and parallel is always, as long as you're on an inclined plane, parallel is always gonna be pulling down the ramp. Always.
Okay,
Good?
yeah.
All right, so is everybody okay with A? You need to write anything more down, or you think you got it?
No, I think I got it. I'm gonna redo it in general.
Okay. All right, B, find the minimum force needed to prevent it from sliding down the ramp. So don't all shut it out, I'm gonna ask you a question. We're trying to find the minimum force needed to prevent it from sliding down the ramp. So first of all, is friction a concern? If so, what kind of friction? And once we establish what kind of friction, which way is it gonna go? So it's a three-part question. So, is friction a concern? Yes. What kind?
Wait, I was looking at the question from the page.
Yeah, so it says,
Find the minimum force needed to prevent it from sliding on the ramp. It is, and, I said it was the static, but that's 162, and it's supposed to be 121.
the answer is 121.
Yes. Is that like the difference
That's
between?
what,
Yeah, that's the unfortunate coincidence. So you're right, static friction is what we want to look at.
Okay.
Static friction is the correct answer. Are you good with that, Eddie? All right, so static friction is going to go up the hill with a force of up to 162,
that's the max.
because that's the max. So what do you need?
Would you find the difference between the parallel and static?
Yeah, tell me why.
Let's take
Okay, so the question is, find minimum force needed. That means how much force do you need to prevent it from sliding? So there's a third force that we're missing.
In addition to the friction.
Okay.
So friction's already trying to stop
It's
it.
like, well,
So
the
friction's
other
going
one.
up at 162, and so then you have to find force of U going up in addition with the friction to stop it, because no matter what, friction's not going to be enough.
Right, so you're helping friction.
Oh,
Okay. We didn't do that another problem we had before, and like today. I think what that was, what.
Yeah, I bet there was a part of 6 that was like that.
Yeah, it was like the difference. Yeah, it'd be the whole algebra problem again, right? That's, I think it comes from.
God, that
Yeah.
is honestly such an unfortunate thing.
Yeah, I know.
And like, it's like I wrote all this stuff down, like the you know I need to do this. Like some of them I have the equation, and then I have all the forces of gravity, and just never connect the dots. Okay, right, that's better than me just thinking. So I'm glad I did. I thought it was more just like what I needed. I actually did so.
Right, so you're. Okay, so are we good with B? All right. C, find the force needed to make the box slide down the ramp at constant velocity. So, same 3 questions. Is friction a concern?
Yeah.
What kind?
So I thought it was kinetic, I think, but it ended up, I got something wrong with the friction I chose. I wrote Y static, but I don't know if it was static or
It's not, it's kinetic.
Okay.
It's kinetic. That's, so the coincidence is, so you're, the answer is 162. By coincidence, that's the same as the static friction.
Okay, that's now I
stupid
remember,
coincidence.
that's what,
That's the stupid
yeah,
coincidence.
okay,
All right, so we gotta come up with 162, but it's for another reason.
okay, yeah.
All right, so the box is sliding down the ramp. What kind of friction do we have? Julia, do you understand why?
Yeah, now I was just, because that's what I thought it was,
What?
but I wasn't.
Right, so what's the word that tells you it's kinetic?
Sliding.
Sliding, right? Are you good with that? Right, which way is the box sliding?
Down,
So which way does kinetic friction go?
up,
Up, and we want the velocity to be constant.
so I got force would be 0.
So, the exact same thing as before, you find the F of U, that when you add it to kinetic friction and F parallel, it gives you 0.
Okay.
Plus friction plus that.
that right there, we just wrote, is pretty much every problem in number 5.
Okay.
The only reason there are so many parts in number 5 is I want you to understand that there are a lot of different possibilities. Sometimes friction goes uphill, sometimes friction goes up down.
Right.
Sometimes it's static, sometimes it's kinetic. If it's moving down the ramp, you might be pushing up the hill, or you might be pushing down the hill. You know what I mean? Like, there's all these different possibilities. Exactly like that.
I
Yeah.
think I missed that.
Oh, no, it was back in about the last lesson. It was the whole problem with the monkey pushing the creative bananas, and the running team comes in, and no one got the few things, and then had to do the bus and the baby, and it's too late. It's monster.
Don't remember that?
I think I'm gonna have to that day.
I think I don't know if that was capital or not.
No, it's great.
Okay. Okay,
Oh my
so,
gosh, I can't wait to finish problem 5 because I actually have so many jelly beans in my house.
oh, good. Well, my 6 hour, since I wasn't gonna have donuts, now that everybody's bringing jelly beans, because you guys deserve it for doing that.
Jelly beans? Oh my gosh, I really want to put a bunch of bean drizzles in like a huge thing of jelly beans and like that.
Bean boozled, what is that? I think what is
I
that?
like the
Oh, it's like a Gates. What is it? They give you little boxes of really good flavors and really bad flavors. But two of them are the same color, so like you'll have like
Is it like a board game
blueberry
or?
or like toothpaste or like chocolate pudding or like canned dog food. It's really good.
Yeah, don't they come in the boxes though? Like,
Yeah,
okay,
little box.
And you can like, I think you can like spin it and it'll like tell you which one to use.
oh, I go ahead with just a box, like jelly bean box on the back. It's like here are two of the same color. One is, popcorn, and the other one's bark.
Like, oh, bark.
Oh, it's like
Okay, should we,
I'm feeling a lot better now. I feel like I know what I'm doing now. It's slightly.
I feel like I'm for sure gonna come tomorrow morning after I've tried them more on my own.
okay. I will be here by 7:05 at the latest. If I'm gonna be here any earlier, I'll shoot out a message on her mind. I can't imagine you to be here before she goes. Sound like me.
so big family house is one of my drivers, so I slept in today. That's nice. So
I don't sleep.
I see that.
so back to it was like 4.1 or whatever, where it was the first of the minutes. I can't remember what now when I was doing the worksheet, but I totally messed up. And I was trying to do the vector addition and maybe some like rote math, but I do that a lot. But with it now, it'd just be like fun to find that stuff. Maybe top 1 and 1 and 2 on this.
On the review sheet, number 1 for sure.
Right, or not 2.
Don't
It
remember
would
number
be
two.
maybe like 3 or whatever. No, it's just 1, I think.
Or two like that also.
So-
Of course, it may help.
But then that would, so I would find the X and Y components. And then,
You okay, Abby?
Yeah, I think so, but I might take an extra break, I don't know.
Okay.
Can I decide tomorrow?
Totally.
Okay. Also, do you have anything, like any other problems?
Extra practice. I will look and see what I can scrounge up. I don't know.
If not, it's okay, because I will prefer you
I'll see what I can, I'll see what I can put together.
I know I'm not gonna be able to I'm glad it's one day of help,
Yeah.
Tonight is,
I have a ton of tests tomorrow.
last,
But think about Thanksgiving break and just sleep.
oh, I am so excited to sleep because I haven't done it
How I feel.
in 3 weeks. Thank you so much.
You're very welcome. I know how hard you're working. If it helps any.
Oh, thanks. Okay, here's Mom.
Okay, I'll see you. Okay, so yes, we found the X and Y
X
component.
and Y. And then from there, would you do like a net force or?
I mean, yeah, it sort of depends on what you know. But I mean, sort of central to every one of these problems is either I'll give you either the acceleration or enough information that you can find the acceleration using like constant acceleration equations, and use that to find your net force.
Okay.
Or I give you all the forces and you add them all together and find your net force. That's every problem is one of those two things. So it sort of depends on what you know. And if I remember right, number 1 is a problem where
So it's the box of donuts, and you want to know how it goes the coefficients of friction, and then you want to know how much force you would need to get the box moving, which is just the equivalent to static friction, which is 100%.
Right.
To get that, so you find the normal force and
Yeah.
using force of gravity, and then B is when you push it at 300 newtons at an angle of 60 degrees below the horizontal, and so you would do 300 for the x would be 300 times cosine of 60, and then the y times cosine, it should be sine of 60.
Yep.
And then from there, and then then you have the force of gravity in y acting downward, and then normal force is this.
The normal force has to be big enough to cancel both of those
Those are
downward
not
forces.
all.
Right, or lift up off.
Right. And then we'll go box. And so would you then you plug this thing back into this normal force back into the friction coefficients, get these two values. And then if the static is greater than 300, or wait, okay, so the answer is box doesn't move. I have the coefficients of coefficients. But would that?
Those are forces.
You're right, those are forces of friction. Would then I use the formula algebra to then find
You don't have any missing forces. I think you know all the forces.
right, so I just try to prove, but that's
What are you comparing it to?
300.
There's the problem. Not all of the 300
Oh,
is
it's, I'd look at, I'd look at,
150.
okay.
Only the 150 is
But it's-
going towards
right,
trying to make it move.
you have to break it up, just like the force of gravity.
it just like that.
Okay.
Parallel will, yes.
Okay. When I first did the work with the 4.1, I tried doing like vector addition, but it wasn't like,
It makes it harder.
right. And so that's why I messed up on that one, and then this one, I wasn't connecting the dots. Yeah. So I think.
Good.
I think so. I think I'm going to go through this again.
I'll see if I can get some of the problems out on my skill too. I can pop up.
Thank you so much.
You're welcome. I hope this helped. Glad you came in.
I think I'm feeling a lot better.
Okay, cool. Well, let me know tomorrow too. Like I said, I mean, if you need the extra time, I'd rather see you take it and do well than, you know, take it at some random deadline.
Okay, thank you.
Yep. Hand it over to you. Marilyn Monroe or Marilyn? Yes. Very cool. I'm glad socks are a thing now. They're everywhere. Socks. Other than everywhere on people's feet and other places.
Yeah,
All right. So you think you're okay?
I think so. I think I just have to go through and like read through the problems and make sure the things work.
Okay.
I'm not doing homework in the kitchen because that's where everything goes down.
I gotcha. Oh yeah, and if you're a family.
Yeah.
I gotcha.
And so.
How old is he? Is he older or younger?
No, he's younger. I'm old, so he's 10. And
Oh,
so it's
gotcha.
kind of like, and we didn't really bug her because we don't really use it a lot. But it's like the only place we could like shut a door unless I went upstairs to my room. So it's just not going to do it. Well,
I gotcha. Gotcha.
so
Gotcha.
I think I'm trying to.
Gotcha. I think you could do, I mean, what's he doing in it? Is he like working or is he like just playing Minecraft?
For all the well, no, he's supposed to be doing homework, but then he watches CD or
Gotcha.
I don't know what he does. I think he makes roller coasters on Minecraft.
Well, that's fun.
Yeah, they're pretty cool actually. So I think he wants to get a roller coaster in here.
That's cool.
I approve of because I like roller coasters.
Me too. I know my son is super into Minecraft and is super excited because he just became 48 inches, which means we can go to Cedar Point this summer. And he's really excited.
You have to go on the morning floors.
What's that?
You have to do the morning floors.
Yeah, totally. Yeah, I don't know. see. He's only 7.
Oh, yeah, that might be much.
But he's also pretty fearless. He's pretty.
Like, my first one was a Blue Dragon, and then when we went with my brother, we were like, we'll do the Blue Dragon. We're like, just kidding, here's the Millennium Force.
Right.
But it was just the greatest.
The blue dragon. That's not even there anymore. Don't that come? Is that the one you're talking about? The one
No,
like that?
or the little tiny blue roller coaster, the like really old one.
Oh, I gotcha.
Yeah, the Blue Dragon.
The Blue Streak.
Blue Streak, right. Yeah.
Gotcha.
Not Blue Dragon. The Iron Dragon is the one that hangs.
Blue Streak is a good one for when we go on physics day because well, never mind, we haven't done circular motion yet, but you're like weightless on that ride, and that happens pretty rarely on the roller coasters. Alrighty, cool. Well, I'll be here in the morning if you need me.
Alright, thank you.
Sure. You too.